introduction to the computational fluid dynamics course. Computational fluid dynamics. So if we need to look into the title, I can break down the title into 3 separate words. The first word is the word dynamic. What is dynamic? So dynamic or dynamics So dynamics is a category that comes under the mechanics. So the general science that actually addressing energy and force acting on body is known as mechanics. So mechanics is actually a science address energy and forces or force effects on bodies. If these bodies are at rest, the branch of that science is actually known as statics. If these bodies are in motion, we call that branch of that science the dynamics. So the word dynamics refer to the motion of the body, or also it's give impression of the time change. So that's the impression that you got when you hear the word dynamics. Either it's motion or it's actually time change. So any study for a moving body from energy and force perspectives, for a body in a motion or a sensation of time change of that energy or that force, that comes under the word dynamics. The second word of that title is the word fluid. What is a fluid? Everyone knows that material has 3 major states. We call them the states of matters, right? And the states of matters are solids, liquids, and gases. Each one of these categories or these matters or these states, it actually has its own characteristics. For example, if we look to these solids, we will find that solids is recognized by small spacing between molecules, which means that it has less freedoms, less degree of freedom to move. So solids molecules have less freedom to move. The second important characteristic of solid is actually the high or the strong bonding force between these molecules. So it has strong bonding forces or force between the molecules. These characteristics actually make solids to become incompressible and it is always hard to reshape a solid body, right? It takes a lot of efforts to be able to do that because that strong shape we can call solids are material with a strong shape memory. It's not easy to change the shape of a solid material. Now let's look to the liquid and gases, and they have very common characteristics for both of them. So let's combine them together and see what are the major characteristics for liquids and gases. So for number 2 and 3, liquids and gases. For liquids and gases, molecules have more freedom to move. That's because they have larger spacing between the molecules, right? Number 2, the bonding force in the case of liquids is less than the bonding force in solids, and also gases is the least bonding force you can find in within the 3 matters here. So both liquids and the gases have less bonding forces compared to the solids. These characteristics give the ability for liquids and gases to actually easy to reshape them, right? So they are easy to reshape. That's why we call liquid and gases, they have really, really weak shape memory. You know that you transfer liquid from a container to another container, immediately the liquid will take the shape of the new container, right? And the same applies for the gas, except that gases are, in most cases, are invisible, right? So with all of these characteristics here, we still also have that liquids are also incompressible, but gases are compressible. So these are the main characteristics or the feature that you can recognize for both solids, liquid, and gases. So now we're still under the question of the definition of a fluid, right? So let's imagine that we have a block of solid material. For example, let's assume this is a copper block, right? And we were able to mark certain number of molecules that aligned vertically above each other. Then I decided to apply a force that's in that direction to try to deform that block. By the way, this force, we call it the shear force. Let's take a side here and define different types of forces. Forces applied can be divided into 2 categories. The first one is force that's normal to surface area. And we call that actually normal force. And this normal force can cause either a pressure or a stress, normal stress. The second type of forces category is actually forces that's actually parallel to surface area. And we call that actually the shear force. And this actually can cause what we call the shear stress. So this force is actually applied parallel to the surface area here. So that's why we call that shear stress. So let's assume that you are applying a shear force over that solid block. If you apply very high value of that shear force, you may recognize some sort of deformation. These molecules will start to move or deform in a certain way. So this is the original location of these marked molecules, and this is the new location of these marked molecules, right? So what happened here, we call that actually a deformation or change in the shape, right? Let's imagine that instead of doing or applying that shear force over a block of copper material, let's assume that we have a water element and I'm applying shear force with looking into the marked molecules. What will happen? When you start applying that shear force, you will notice that there is deformation happening with the recognized by the motion of the molecules. But if you keep that force applied to that water element, you notice that deformation will continue. Molecules will continue to move. So you start from that marked location here. This is the initial deformation. Then the deformation will continue as long as you keep that force applied over that water or liquid element, right? So from that, we can come with a definition that explains what fluid is. You can see that substances that continuously deform under the action of shear force of any magnitude. I think I missed the spell. Look, this one is magnitude. So this is the book definition of a fluid element. Substances that can continuously deform under the action of shear force of any magnitude. If you noticed for the solid material, right, when we applied that shear force over that element or that block, what happened is you experience what we call it an instantaneous deformation. And you also can imagine how big the magnitude of that force that you need to apply for that copper block to be able to deform it, right? So when you apply that huge quantity of force over that copper block, you will have an instantaneous deformation, but the material will not continue to follow your hand and deform. I maybe picked up some of soft material like copper. If you're looking for steel, that's going to be harder and harder, right? Try to think about applying that force to a wood, a piece of wood. You think that the piece of wood will continuously actually deform under the applied force? It's not going to do that. While in the case of the liquid, which I picked up water as an example here, the presence of the force will cause a continuous deformation. And we can imagine that how much the magnitude of that force compared to the force applied to the solid one, right? So that's definitely much less force magnitude that you can or you need to apply for that liquid. If you are imagining that cubical shape of gas, made of gas, that force would be much, much, much smaller. So the outtake of that here, we can look into the material under two categories, right? And the liquids and gases These are the two states of material that can actually satisfy the definition of a fluid. And liquids, gases can be continuously deformed. So the word continuously, that's very important here, can continuously deform under the action of shear force of any magnitude. These two conditions is these are the conditions that exclude solids out of that. So in a short summary here, after knowing the definition of a fluid, these are the materials that can continuously deform under the action of shear force of any magnitude. Fluids are simply the liquids and gases that exist. So any liquid or any gas are defined as fluids. So that's the second term in the title of that big title, Computational Fluid Dynamics. So now we know that dynamics is a science dealing with energy and force effect on moving bodies and count for the time change. The word fluid is indicating substances that can deform continuously under the action of shear force of any magnitude, and that's combined both liquids and gases together. So the last word of the title is actually the word computational. So the word computational give you the sensation of mathematical analysis, math analysis, right? But also give you the sensation of computational tools, computing tools, right? Like tools, which mean that I'm looking for computers, right? So now if we combine the three words definition, we can simply say that computational fluid dynamics which usually we refer to as CFD. If you want a very simple definition to that, it's actually an approach. In a simple word, it's an approaches to solve fluid flow problems. So it's a method to solve fluid flow problems, and now we know what's the definition of fluid, right? And if you want to extend that definition a little bit, we can say that computational fluid dynamics is actually a mathematical analysis of fluid flow, and the word flow can be transport, and that's what's coming from the dynamic word in the title, right? To understand the fluid behavior when I say the fluid behavior, we would like to look into two specific things here. We're looking for the energy transport, and we're looking for the hydrodynamics. So energy, we're looking for temperature, right? And for hydrodynamics, we're looking for pressure and velocity, right? These are the major parameters that we're always looking for when we do the analysis of a fluid flow problem. Now, if we want to look into the standard book definition, you will find more details more than that. But this is just to give you some brief definition of what computational fluid dynamics is. So in a simple word, we are using math to try to understand the behavior of a fluid under transportation, looking for the energy transport, looking to the mass transport within that fluid under different conditions. That's simply that definition. And next, we will put the book definition of CFD and look for some specific terminology that's always used in the science of CFD. So let's look into that. I'm going to rephrase the definition in using different words here. And the reason I'm doing that because I will expand the definition of CFD to look into some of the common terms or terminology that we use in CFD. So if we want to give the extended definition of CFD science, again, it's the science of simulating a system slash a design slash a problem mathematically using models and solve these models either analytically or numerically, or the other approach is to build a prototype to investigate experimentally for understanding fluid behavior under transport or flowing conditions. And again, when we do the word fluid behavior, we're looking for the energy and mass transport, right? So the reason I extended that definition here, because there's a few words that we would like to highlight in that definition. You will find that the word simulating, that's a key word in that definition. You will find the word design or system or problem. You will find the word models. And also you will find that the fluid behavior under flowing condition here means that we are trying to do some analysis for that fluid flow. So I would say the understanding is the second definition here, or I'm actually the second word, or I can actually replace that with the word analyzing. Or do the analysis. Says, okay. So let's have that word analysis also highlighted here. So there are a few words here, keywords that mention into that definition here. So let's highlight these words here. So the first word I'm interested in is the word design. I will define what is design. Then the word models is also important. Then the word simulation is also important. And analysis is another keyword. So first, what is a design? When we are doing that CFD analysis, again, to simulate a design or a system or a problem. So the design in a simple word is an idea it's a device, or it's a problem you are interested to investigate. This is the definition of the word design. Now, so the science of simulating a system design problem or a problem mathematically using models. What do you hear by what the word models here is giving you the sensation of? It's actually, it's a way, it's a method to describe your design. And it is clear from the definition, this is could be one of two things. It could be mathematically or experimentally. So the model here could be through mathematical analysis. So you can do that mathematically. Or experimentally. Then you need to, after you come with an idea, then you decided which way you're going to go for picking up the model to describe your design. You can describe your design by picking up some mathematical equation that describe your phenomena, or you build a prototype to investigate that idea or that device experimentally. But again, we're going to simulate that. So how we're going to simulate that? What we do in the simulation is to find a method to assemble your models to solve this if we are following the mathematical one, or build a prototype to conduct experiments. These are the two approaches that you follow to understand your idea or your device, or simulate your idea or your device, right? Then the purpose of the simulation is to actually produce results and data from simulation for or to assess your design, maybe evaluate, could be another word, right? Or to optimize your design and go back and change your models and change your simulation, performing more experiments if you are doing that experimentally. So I would add the word optimization in here. So in summary, you have an idea, you have a device in your mind, and that's to address a specific problem. Then you have to describe your idea or your device or your problem. You could do that using mathematics, or to do that experimentally. If you follow the mathematical way of describing your idea or your design, you have to find this equation presenting your design, and to assemble these phenomena together, these equations that describe your phenomena together. Or if you are actually seeking the experimental path, you have to build a prototype to start conducting experiments. Either you're simulating your design through mathematical models, or building a prototype and experiments, you will end up getting results and some data from your simulation. Then you can look into this data to analyze it and to assess or evaluate your design. Is it good or bad? It's need improvement. So we're gonna improve the design through back and forth process, or you optimize your design for a better performance, maybe for cost effectiveness, maybe for space limitation. It depends on what parameter you need to optimize your design for. That's the extended definition of CFD and some of the basic terms that we use all the time. You're going to hear these terms all the time when you get into that CFD field. So in the next, I would like to start looking for the major processes in CFD. How we can actually look into the CFD as a process, what are the sub-processes that we can or we have to use to go from the design all the way to the analysis and complete the CFD process. So let's go into that.